Hi, today we'll talk about section 1.4, which is digital logic circuits. So we will analyze how logic circuits, how the outputs of the logic circuits depend on the inputs, and basically we'll use the machinery that we developed in the first three sections. Actually, we'll use propositional calculus. So generally, when we do digital logic circuits, we'll think of the switches connected in the network. Switches connected into circuits. And connections will be performed by three connectors. Here is the AND one. This is the one that we call AND. This is the one that we call OR. And here is the one that we call NOT. Oops, OR has two inputs. No. Please pay attention that each of these gates actually has two inputs and one output. Here also two inputs, one output, and then here just one input and one output. And how do these gates work? They work basically the same way as AND, OR, and NOT connectives in the propositional calculus or operations, and that means AND the gate will provide the signal will be on just in one case when we get both inputs to be on. And then this basically also corresponds to the serial connection or connection in series. Then this OR will just behave the same way as our OR in propositional calculus. That means we'll get on signal if one of these inputs is on, one or both. And finally, NOT is just like a converter. If we get the signal here, if it's on, then if input is on, output is off. If it's off, output is on. It just converts to the opposite stage. So let's see how. So generally, what we do, we just have switches connected in the net using these gates. So here's one example. So as an example, so we'll have something like this. So here is the OR, and then here are two signals. We'll call them P and Q. And then here is the other one. It's called Q and R. Q and R are here. And R. Then we have inverter. And then these two are again connected. And they are connected with the OR. So when you look at this circuit, generally it's obvious that we have three switches, P, Q, and R. Since I use the same letter, then Q obviously must have the same status, on or off, which is the same valuation, 0 or 1, true or false. And then what? Then P and R have their own independent status. Generally, what we do very often, to just simplify the writing, we think of one source for Q. So sometimes, and more often actually, we'll write it like this. We'll just think of the Q here, and then Q will just will feed on both spots. So there is just one place where we kind of provide the signal or provide information on the signal, and then it branches. So whatever status is there, the same status is provided everywhere. So the question, what we ask you in this problem is, if all three of them are 0, what will happen at the end? So that means all three switches are turned off. What happens at the end? Are we gonna get on or off status? So what will happen, since P and Q are both zeros, then the junction here will give us a 0. And then here, conjunction Q and R will also give us a 0. Here. But then inverter will make it 1. So at the end, we'll have 0 or 1. So we'll have 1. So at the end, we get on signal at this valuation or this choice of values for the input. The output will be 1. So what are the things that are interesting here? It is just we want to connect this with the technology that we developed in first 3 sections and see how that applies. So it should be a fairly simple section, just nice application of what we need before. So what happened here, we had a circuit, and then for a particular valuation, we kind of calculated basically the output of that circuit. And then in order to connect with the propositional formulas, let's see one example where we have propositional formula and we are asked to provide the circuit corresponding to it. So here it is, P and not Q, or not P and Q. So how do we write draw a circuit? So we start with P and Q. So in order to build the top one, we'll just lead P normally, but then Q has to go through inverter. So here is now not Q. These two will feed into OR symbol, sorry. And since symbols are similar when I draw, I often like to write the word inside so that I'm sure that there is no misunderstanding. So this is P and not Q. Then, as I said, I don't have to write these two inputs again. I'll just lead them from this position. So now P, I will lead P down. So here it is. Now P will go through the inverter. Here it is. Now it's ready. Q will now be led directly before the inverter. So here is Q, and now they are ready for AND. So here is that second AND, and of course at the end you just connect them with the third color. And then you just connect them with OR. So here they are, here they are. And here is your net. So you start with, as I said, I don't mind if you make copies of P of Q, if you don't like leading them from the same spot. It's basically the same thing as long as you use the same letter, then we know that they must have the same on-off status. Maybe I didn't mention it specifically, but I assume you know that when the switch is turned off, we label it with 0. When it's turned on, we label it with 1. I already used that, but I forgot to mention it specifically. All right. So we accomplished 2 things. How do we find the status of circuit for a particular choice of inputs, and then how do we make a circuit corresponding to certain propositional formula? Of course, the process can go backwards if you have a circuit, you can recognize it and write the formula. Works in both ways. So basically, here's our plan, and that's the only thing that's left in this section. Basically, it's very a short section. We are most interested in it to serve us in the section 1.5. What we want now is the following: when we get a particular demand, particular practical problem that asks to build a certain type of circuit, how do we build that circuit? And in order to develop a strategy, basically an algorithm that does that, we first need to understand very important notion of something called a recognizer. So please pay attention to recognizers, because that's the crucial thing for our strategy. So here's the definition. A recognizer is the circuit which gives value 1 for only one combination of input signal. Combination of input signals. And that's why the name comes, because actually that recognizer is the circuit that recognizes that combination. So if I see recognizer, I can tell you which combination it is, and the other way around, if I see the combination, I can tell you what a recognizer is. So how do you build a recognizer? Here is it's an example. Example 143. 143. Find the recognizer. A recognizer for the combination on inputs P equals 0, Q equals 0, and R equals 1. So basically the strategy is very simple. When you here's the recognizer. It will be a conjunction, because conjunction is true only for the one choice of its components. So what do we do? Since there are 3 of them, there will be a conjunction of 3 expressions. What do we do? Since P is 0, I will not take P, I will take not P. Since Q is 0, I also have not, I'll take not Q. Since R is 1, I'll just take R. So basically, if the value of the input is 0, I take negation of that letter. If the value is 1, I take letter itself. Why is that doing what we promised to do? When is this true? Obviously it's true if and only if non-P is true, not Q is true, R is true. But not P being true, that means P is false, Q is false, and R is true, which is exactly R0, 0, 1. Of course, this is 0, this is 0, this is 1. So that's actually a very easy way to make a recognizer. Once again, it's a conjunction of either letters or their negation, and you decide whenever you see a value 0, you take a negation. Whenever you see value 1, you take the letter itself. And let's see how will that serve us to construct particular circuits. So here is an example. We have 3 switches. And they say design a circuit so that the bulb is off when they are all off. So bulb off when they are all off. And then what? And every switching of an individual switch. Every switching of an individual switch changes the bulb status. This is a practically interesting problem. This is just like if you have 3 floors and they all feed the same bulb, and then every time you turn off, you just press the switch on one of the floors, status of the bulb changes. If it was on, it will be off. If it was off, it will be on. So how would you connect those 3 switches so that it does what you want it to do? So here it is. Basically what you want to do, you will make a table. And in that table, you will actually record all the valuations, and that will tell you what we need to do. So here is P, Q, and R. And then it could be, did I put? No, I did zeros. So generally I'll start with all 3 zeros. And then 0, 0, 1, 0, 1, 0, 0, 1, 1. Then I have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Here they are. There are 8 of them, as we know. So here it is. Now I don't know what the formula I need. Actually, just I know the values. So here is the value of the formula. When there are all 3 zeros, it will be 0. Why? Because that's what we said. Bulb is off when they're all off. Now, what did I do here? I switched the status of R. That will make it 1. So from switched off. Here, I also, from the basic situation, I switched to one switch, so it will be 1. This one, what? 2 of them were switched, so that's 0. Then here, only 1 is switched, so that's 1. 2 of them are, only, yes. 2 of them were switched, so we're back to 0. 2 of them switched back to 0. 3 of them switched, that will be back to 1. Alright, yes, I corrected that correctly. Now what? Now you just record those that have 1s. I don't want this one. I want this one. I want this one. I want this one. And I want this one. And then what do I do? For each of them, I will make its recognizer. So recognizer for this line would be not P, and not Q, and R. Or, and then you take this junction of all the recognizers, because what? Each of those recognizers guarantees exclusively value 1 on particular line. And since you want to have value 1 of one of those 4 lines, you actually do the junction of the recognizers. And then what would that be? Or P and then not Q and R, or P and Q and then not R, where, no, I'm cheating here. Let me see. This recognizer is here. This recognizer has a negation on Q. No. Sorry. So this one has what? A negation on P. Root on Q and negation on R. The second one. Negation on P, through on Q, yes. And negation of R. This one has through on P and negation on Q on R. So let's see. R is the only one through. Q is the only one through. P is the only one through. Yes. So I check these three lines, and then the line where what or all three of them are through P and Q and R. Here it is. So generally, once again, you draw the truth table. You check which lines have the truth value 1 according to your needs of your design. Then for each of the lines you draw a recognizer. Once again here, P was false, you put negation, Q was false, you put negation, R was 1 or true, so you put R itself. The same thing for the other two. The last one has all three ones. Here is the formula that's true on these 4 lines and no other lines. And then if you want to draw the circuit, that should not be complicated. Let me just make a little space here so that we can draw a decent circle. So generally, what are we gonna do? We'll take P, Q, and R. And R. So first one will have inverter on P. Here it is. Then Q will go directly, and R will go directly. And then here's a little abuse of notation. I cannot feed 3 things into this junction, okay, let me do the first one correctly into conjunction, and then the other ones I'll do the shortcuts. So here is AND, provide something, and provides AND again. And that one goes down. So generally, instead of writing this, sometimes you will just do abuse of notation and think of a gate that has 3 inputs and then provides AND output. This is just to make things a little shorter. That I hope should be okay. This is just like a shortcut gate. Alright, so that's the first one. Second one will do the same. The only difference is oh no, second one needed inverter on Q as well. So here it is, and then actually I'll do the inverter on R as a down. I didn't use it, but they are all ready now. And then what? On the second one, what will I do? I will use inverters on P and R, so P will be connecting after the inverter. Then Q will be inverted, will be used before the inverter. It gets a little messy sometimes, I agree. And R will be used after the inverter. Here they are. And as I said, I'll just make one M symbol here, just as a shortcut for this. That's absolutely okay. And then on the third one, let me do that blue. Q and R will use inverters. So here is the Q inverter. So P will not use the inverter, so P has to go before inverter. Q will use inverter, so after the inverter. And then R also will use inverter, so I connect after the inverter. Here is that. Finally, the last one will just use all 3 of them directly. So let's say, alright, go down directly, go, where is R, R is here. Directly all 3 of them. So here it is, I have all 4 pieces, and now I will connect all 4 of them. Again, abuse of, it's just a little shortcut. So here I'll do OR. Here it is, here is the gate that does what you need. So here are the inputs, so let's say something is fed and they're a little longer. So here it is, P, Q, and R are there, so whatever inputs are coming into P, Q, and R, the output will be the way we expected. Alright, and then the last comment is the same way as formulas are sometimes equivalent, we also have that circuits are sometimes equivalent. So here was an example. When are 2 circuits equivalent? If they always provide the same outputs for every if they provide, whenever we feed the same combination of input, they provide the same output. Why is that interesting? Because sometimes if you have a few equivalent circuits, you would rather use the one that's less expensive, and there is a whole theory in the circuits, here circuits, where they actually give you strategies how to choose the most economical one, but that will not be part of our discussion. So here is example 1, 4, 5. Here are two circuits. So here is, P went through inverter, and that was fed into Q as well. So here is Q. So this is connection from P. Here is Q. Here is AND. Then there is inverter. And then P was, not P was fed here. So here it is. And then I have AND again. So here is one circuit. And here is the other one, PQ. And then the inverter. So obviously, if they do the same job, you would rather use this circuit because it's much less expensive to construct. How do I show that they are equivalent? Generally, the easiest way is just to recognize the appropriate formula and then to show that formulas are equivalent, building the truth table. So what would that be? So this one here, this is not P and Q. Then it was inverted here. And then we have AND, not P. What about this one? This is P or Q, and then negation. So let's see, are they equivalent? We are asking question. We can either make a truth table or just use the equivalency that we already learned. I'll go distributive here. So this will be P or not Q. What did I do here? I used De Morgan's law and became or. Negation got attached to negative, so double negation gave me P, and then negation got attached to Q. So this would be P and not P, and that would be equivalent to P and not P, or not Q and not P. P and not P is always contradiction, so it's always false. False or anything is that anything, so this is equivalent to not Q and not P. I can factor out negation using De Morgan's law backwards, and we got exactly, of course, with commutativity, negation of P or Q. Here is the other circuit. So we proved that those two formulas are equivalent. That means that those two circuits are equivalent. Okay, so this section is really mostly designed to help us to kind of get ready for section 1.5, where we will discuss more how to use logic circuits to add, subtract, add integers, so that would, which is a very important operation to be executed by the processors.